All right, it seems we've reached a tapering of the people joining. So I'll go ahead and introduce our speaker today, which is Dr. Nathan Giha, recent graduate of the Department of Nuclear Engineering over at the University of Michigan. And he's going to be telling us about fission, neutrons, and gamma rays. So go ahead and take it away, Nathan.
All right, thanks, Kyle. So, first of all, if you have a question, the best way to get it answered is to write it in the Q&A section on Zoom. Uh, if there is a slide that is relevant to your question, go ahead and include the slide number uh, with what you wrote, and then Kyle will let me know. We can stop and answer it. Uh, if the question you have is not related to the presentation or the current topic, go ahead and wait until the end to put it in the chat. All right. So this week of the summer school is Fission Week. And yesterday, Kyle told you all about fission, which is the first step of fission. That's the time when one nucleus splits into two. Today, we're going to talk about the next step where you have two nuclei and they're very excited and they de-excite by emitting particles, mainly neutrons and gamma rays. So we'll talk about that today. And tomorrow, Dr. Ramona Vogt from Lawrence Livermore National Lab is going to tell us about studying the fission process with measurements of these particles. So, de-excitation today. A quick review. Kyle showed some of this yesterday, but fission happens in the following time scales. At around 10 to the minus 20 seconds after it starts, we end up with two fragments. And then for the next period of time, usually takes about a nanosecond or so, but we can go longer. We emit neutrons and gamma rays. And then there's some stuff at the end here that can take a really long time that's related to beta processes. So we'll talk about that a little bit later. Here's a little cartoon of the fission process. If we can wait for it to start again, we have the nucleus splitting. The fragments fly out in opposite directions, and we get emission of neutrons and gamma rays. So this is what Kyle talked about yesterday, scission. We have a nucleus that's vibrating or has some external impetus, like an incident neutron or photon, and it goes over this potential energy barrier and eventually proceeds to split. And we get a lot of energy out of that. The fragments themselves possess a lot of kinetic energy on the order of maybe 160, 170 MeV. That's total kinetic energy, or TKE. But they also have some excitation energy, and that'll be important to what we talk about today in the particles that are emitted, this total excitation energy, or TXE. It's maybe 20 to 30 MeV, but it depends. The total amount of energy, or the sum of these quantities, changes for each fission event. It's not always, I guess in this case, it would be 200. Sometimes it'll be 220, sometimes it'll be 240, sometimes it'll be 170. Similarly, the partition between kinetic energy and excitation energy can change depending on the event. So all that is to say, you're going to get a distribution of excitation energies. It's not always going to be 30 MeV or some other number. We promised to talk about neutrons and gamma rays today, so I want to introduce those particles. You've probably seen them earlier in the summer school, but let's do a quick review. The discovery of the neutron by Chadwick in 1932 kind of marked the beginning of the field of nuclear physics, one could say. And the neutron itself is probably pretty familiar at this point. It's very similar to a proton. If you're familiar with the concept of isospin, there's a symmetry with the proton, where the proton has an isospin projection of +1/2, and the neutron has a projection of -1/2. Its rest mass is a little bit under 1 giga-electron-volt. It's 939, maybe 941 or so. It has no electric charge, and that's the most important thing to know. You need to know about it from an electromagnetic standpoint. There are some interesting topics in electromagnetism and neutrons, though. It has a magnetic moment, so it can be affected by magnetic fields. And it may have an electric dipole moment, but this is an open research question. And then, of course, it's a fermion, meaning it has half-integer spin. In this case, it's an intrinsic spin of 1/2. So that's about it about the neutron. The most important things I want you to remember are that it has a significant rest mass. It's about the same mass as a proton, and it's a neutral particle, electrically speaking, so it doesn't interact with electric fields. Gamma rays are just photons that come from a nucleus. So it's the same exact particle as radio waves. So listening to the radio, those are photons that are at very long wavelengths and are emitted by a radio tower. You might listen to music or something. Microwaves, maybe to heat up your chicken tenders. Of course, our visible light, also photons, UV, all the way up to X-rays and gamma rays, all the same particle, photons. We call them gamma rays just because they originate from a nucleus. That's the meaning of the term. These, in contrast to neutrons, have no rest mass, and correspondingly, they travel at the speed of light. And in a vacuum, that's pretty close to 3 × 10⁸ meters per second. Similarly to neutrons, they also have no electric charge, and they are bosons rather than fermions. They have an integer spin. In this case, it's 1. And if you're familiar, they're the force carrier for the electromagnetic field. Photons are. So neutrons and gamma rays. Yesterday, we left off with at about this point where we have a big nucleus. It separates into 2 smaller nuclei, and then that's scission. We're not going to talk too much about how we arrive at that point today, but Kyle introduced some of them yesterday. You can have induced fission. Induced by what? By pretty much anything. The most common is a neutron-induced fission. You might have like a uranium-235 nucleus that captures a neutron, and then it has enough energy to get over that potential barrier that I mentioned a few slides back. You can also introduce that much energy with other means, though. You can have it absorb a high-energy photon. You can have it absorb a proton, deuteron, and so on. There are also some nuclei that will fission spontaneously, or every so often they will tunnel through that potential barrier and fission can occur. But ultimately, we're left with these fragments that have a decent amount of excitation energy, maybe on the order of 10 MeV. It can be a lot more than that, though, or maybe a lot less. A decent amount of angular momentum on the order of 6 to 8 h-bar. Again, it can be a lot more or a lot less, though. And moving pretty fast, on the order of 3 to 5% the speed of light, maybe a little more. So we in the fission field really like this style of chart to visualize the excitation of a fission fragment. And before I add things to the chart, I want to point out the axes. On the vertical axis here is the excitation energy of a fission fragment, just one. On the horizontal axis is the angular momentum of that fragment. And there's a shape here. What that means is that when we have a fission occur, we get a fission fragment, and it might be somewhere in this shape. So it could have a variety of angular momenta and excitation energies. Of course, this isn't really to scale. You can have a big range of these things, but it gives you the idea that it's not always, the fragment isn't always born in the same point on this graph. So after fission, the first thing that occurs if energetically available is neutron emission. That's because neutron emission is governed by the strong nuclear force, which is the strongest force that we have available to us. And it also happens to remove a whole lot of excitation energy. So there are a couple components to that excitation energy removal. The first is the neutron binding energy. For fragments that we're interested in, that could be in the range of maybe 5 to 7 MeV. And that's energy that you remove from the system, which is the goal of the excitation, to remove energy from the system. That's just what you remove energy from. That's how much energy you remove just by getting rid of the neutron. That doesn't even take into account the kinetic energy that that neutron might have. Depending on how much energy your fragments ended up with, you might get around 3 to 4 neutrons per fission on average. It depends on the system. If you have a Californium fission, you get on average about 3.7 neutrons. If you have plutonium fission, it's only about 3. And the neutrons follow this sort of spectrum where you're most likely to get a neutron of around 1 MeV, but there's this long tail where, with decreasing likelihood, where you can get neutrons of pretty high energy. The average is usually around 2 MeV. And again, this happens pretty quickly. By the time you get to 10 to the minus 15 seconds, you're probably done emitting neutrons. A couple other important details about neutron emission. They're emitted approximately isotropically in the frame of the fission fragment. So if you were able to fly alongside the fission fragment, you would see that neutrons are emitted in each direction with equal probability. But we know that fragments are moving pretty quickly, on the order of 5% the speed of light. So while they might be emitted with equal probability in every direction, if we were flying alongside the fragment, if you zoom out and to a frame where you see this fragment moving, well, actually the neutrons are going to be focused in the direction of the fragments. And that results in an angular distribution that you might see here, where neutrons tend to be emitted in similar angles to each other, this side of the graph, or opposite angles to each other, this other side of the graph. And that's along the fragment directions of travel. So we started out up here with a lot of excitation energy and angular momentum. We emit a couple neutrons from our fragment. All of a sudden, we have a whole lot less excitation energy. So neutrons take away a lot of excitation energy per neutron. That's the 6 MeV from the binding energy, another 1 MeV or so from the kinetic energy. And you've got quite a bit there. And neutron emission will occur usually until it's no longer energetically available. You reach a point where you don't have enough energy to emit another neutron. It costs quite a bit, that binding energy. So at that point, we're left with some excitation energy and potentially a lot of angular momentum left. Our goal, of course, is to get to the ground state of the fission fragment, which is usually around this point at zero excitation energy and lower angular momentum. How do we accomplish that? Well, neutrons are no longer an option. Now we emit gamma rays. So again, we got rid of a lot of the excitation energy with that neutron emission, but the nucleus still has a lot of angular momentum, or J. And what I show on the right side of your screen is what's called a nuclear level scheme. Based on the structure of nucleons in the nucleus, you can rearrange or excite different nucleons to get to higher energy levels. And when you don't have that much excitation energy, that density of states is pretty low, and you can make graphs like this that show you what the energy levels of the nucleus are. So once we get down a little further down in the excitation energy regime, we can start to see specific gamma rays with characteristic energies. Now, I mentioned we have not too much excitation energy left, but quite a lot of angular momentum. That implies then that gamma rays remove most of the angular momentum of the fragment. After neutron emission, we might still have a decent amount of excitation energy, maybe a few MeV. And so we'll emit what are called statistical gamma rays that are kind of random energies. But we'll also emit these ERAS gamma rays that are along these rotational bands, they're called, in the nuclei, and those remove a lot of angular momentum. So this gamma ray emission process goes until maybe a picosecond to a nanosecond after fission, usually. Sometimes it can be longer. And depending on how much angular momentum you started with your fragment, you could end up emitting a lot of gamma rays. The average gamma ray multiplicity for familiar fissioning systems for the whole event is around 6 to 8. So that corresponds to maybe 3 to 4 per fragment. But you could get a whole lot more depending on how much angular momentum you started with. So now we have our chart kind of filled out, this fragment de-excitation. We have neutrons up here, and then some statistical gamma rays here that remove a decent amount of energy and then a little bit of angular momentum. And then we have this regime down here with gamma rays that don't remove that much energy, but do remove a whole lot of angular momentum. And Dr. Ramona Voigt's talk tomorrow will go into great detail about how you can measure the angular momentum of fission fragments by looking at this photon emission down here. So that's how a fragment de-excites. While energetically available, it'll emit neutrons, and those neutrons, the neutron energies follow some sort of spectrum. Then it'll emit, while it still has a decent amount of energy, but not enough to emit neutrons, some statistical gamma rays, and those gamma rays will also follow some sort of smooth spectrum. Once you get down to sufficiently low energies, the gaps between the nuclear levels become large, and you'll emit discrete gamma rays that have identifiable energies. And those remove a lot of the fragment's angular momentum. So I mentioned that these quantities can vary quite a bit. Even if you start with the same nucleus every time, for example, if you have uranium-238 and spontaneously fissions, you can get a pretty big range of these quantities. And that is because the emitted neutrons and gamma rays depend a lot on where we start on that chart. That's the initial state. There are also ways for us to affect the initial state externally. For example, this graph shows neutron multiplicity as a function of incident neutron energy on this axis. And you can see that as we increase the energy of the neutron that induces fission, we get more and more prompt neutrons out of the fragments. That's because we're adding energy to the system this way. And correspondingly, if we add energy, we might get more excitation energy, more neutrons emitted. Just from the variance, though, of fission events, if we have more kinetic energy, then the fragments themselves are moving faster, and the neutrons that those fragments emit will be boosted more. So we might measure the neutrons we have to have more kinetic energy. If there's a way for us to add more angular momentum to the fragments, or if it just happens randomly, we might get more gamma rays. So for the next couple slides, I'm going to show some experimental results where the initial state was affected or measured somehow, and then correspondingly how that affected the emission of the neutrons and gamma rays. So on this slide, on the left here, we have gamma ray multiplicity, this section on the top, as a function of the excitation energy of the compound nucleus. And it's kind of difficult to see in this graph, but the blue points tends to increase with increasing excitation energy. That tells us that as we add more energy into the system, in this case, we get more gamma rays. Similarly, this is with a different type of experiment where you can measure the incident neutron energy, looking at the black points here. As you add more and more energy to the system, again, you get more gamma rays. So both of these show that as you add more energy, you're getting more gamma rays. Here are a couple other experiments, experimental results. The one on the left shows that as you decrease the total kinetic energy of your fission events, so the kinetic energies of the fragments, you get more and more neutrons. And this is true for a variety of different fragment pairs. This one over here shows that as you increase the total excitation energy of the fragments, so that's the complement of the total kinetic energy, is the total excitation energy, you get, for gamma ray multiplicity, it kind of depends. In some cases, you can see that there's a positive dependence here with the blue points. In other cases, it seems pretty flat, like the red points here. So in this case, less total kinetic energy means more total excitation energy equals more neutrons. That seems pretty straightforward. In contrast, you get more excitation energy here. More gammas? The answer is it kind of depends. And this is pretty recent, so this is an open topic of research. Now, up to this point, I've talked about emission of prompt neutrons and gamma rays. And that word prompt means that it happens right after the fission. Those timescales we were talking about, by the time you get to a nanosecond after fission has happened, you've emitted basically all of the prompt neutrons and gamma rays, depending. But we see the effects of fission long after that. And that ends up being really important for some technological applications of fission. So those prompt emissions are governed by the strong nuclear and electromagnetic forces. Strong nuclear force, neutron emission; electromagnetic force, gamma ray emission. But there's another force that is important in fission studies in some avenues. That's the weak interaction. A common example is that you might hear if you're studying nuclear fission reactors is cesium-137. There's a lot of cesium-137 produced in fission reactors, and it's unstable. Well, it's stable against strong decay and electromagnetic decay in its ground state, but it's unstable to weak decay. So a lot of you might see cesium-137 and think of a 662 keV gamma ray. That it's really strongly associated with that. Well, that gamma ray doesn't actually come from a cesium-137 nucleus. It comes from the nucleus that cesium-137 beta decays into. So if you have a cesium-137 nucleus, maybe produced in fission, it decays by beta minus decay to barium-137. A large portion of the time, it decays to an intermediate state of barium-137 that is excited to 662 keV, and that's how you get that gamma ray out. So this process of delayed emission, it corresponds to gamma rays like this, but it also corresponds to some neutron emission. If you've heard of the term delayed neutrons before, that's the result of a similar process where you get a fission fragment, it decays by prompt emission to probably its ground state, and then it beta decays to some other nucleus. Now that other nucleus might emit more gamma rays, or it might emit a neutron. And that's where these delayed neutrons come from. And these are really important for controlling fission reactors. If we didn't have delayed neutrons, it would be very difficult to design a fission reactor. Of course, in less exciting news, this delayed emission is responsible for the long-lived radioactivity of nuclear waste from fission reactors. Here's an example of the half-lives of different fission products from nuclear fission, where part of the fission products have half-lives on the order of a few years. Some of them 10 to 100 years, some of them up to 300,000 years, and then some really long, millions of years. Of course, nuclear waste is.
Hey, Nathan, we've got a question.
Oh yeah.
Mind. Why are neutrons emitted from a fragment during de-excitation instead of protons?
That is a very good question. The reason is because fission fragments are very neutron rich. I wish I had a picture of the nuclear chart, but if you are familiar with it, you'll see that as we grow to heavier and heavier nuclei, if you want to keep a nucleus stable, you need to add more neutrons than protons. Protons, of course, are all positively charged, and so they repel each other. Adding more neutrons can give you more strong nuclear force to bind a heavy nucleus together. But when you get this very heavy nucleus that has maybe 240 nucleons, a large portion of the neutrons, and then you split it apart, all of a sudden you're left with two smaller nuclei that have a lot more neutrons than they want to have. So in that case, it's much more energetically favorable for them to emit neutrons than to emit protons. So that's why neutrons instead of protons. There's another question: why delayed neutrons are important for controlling reactors? They're important because we because it's an engineering challenge to respond to very small changes in the multiplication in a reactor very quickly. And delayed neutrons give us a lever to control that on longer timescales. So in a fission reactor, you're aiming for a steady amount of fissions to occur. You're trying to sustain a chain reaction so that fissions emit neutrons and those go on to induce other fissions that emit neutrons. You're trying to sustain that chain reaction without having a runaway reaction where you're getting more and more fission as time goes on. If we were just relying on prompt neutrons to do that, well, prompt neutrons are all emitted within 10 to the minus 15 seconds of the fission. And they, in most fission reactors these days, they have to slow down, but that's a really short time scale. If you want to put in a control rod to control the amount of multiplication, it's a whole lot easier to do that if you have a longer time scale. So these beta delayed neutrons that might get emitted, several seconds or minutes or longer after the fission occurs, give us this neutron source that's a whole lot slower. Still contributes to multiplication because those neutrons can induce fission, but a lot easier. Can the C's get used in case of supercritical state K effective greater than 1? Can the cesium get used? I don't quite understand the question. In the case of a supercritical state where you have a runaway reaction, you will make cesium, and it will still decay and produce these gamma rays, but you have a pretty big problem if your K effective is greater than 1. For if you're supercritical. Okay. So delayed emission. Maybe not that interesting from a studying fission perspective, but very important for applications in fission and whether they're feasible. Okay. Speaking of applications of fission, why do we study these things? Why do we study neutrons and gamma rays from fission? One reason is just to improve our understanding of fission. It was discovered at this point over 80 years ago, maybe even over 85 years ago by now. And yet, we're still trying to answer some questions about it. For a reaction that's been so heavily studied because of its applications, because of its various uses, that might come as a surprise, but there's still some things we don't know about it. One of those things we don't know is what are the initial conditions of these fragments when they come out of scission. And it's very difficult to measure that. And really the only way we have access to those quantities is by measuring the neutrons and gamma rays that come out. Other interesting applications. This is kind of basic physics adjacent, but about half of the nuclei heavier than iron in our universe are produced via the R process of nucleosynthesis. So this is an astrophysical process that happens when two neutron stars collide with each other. And it turns out that you need to have a good understanding of fission to understand the amounts of different elements that would come out of this process. So there's some collaboration between the people who are studying these nuclear astrophysical sites and people who are studying fission to try and make good models of that. In the non-proliferation sphere, neutron and gamma emission are unique signatures of special nuclear material that could be used to make a weapon. And it's important for us to understand the characteristics of that emission, such as how many there are, how much energy they have, and what angles they're emitted with respect to each other, to accurately quantify what we're looking at. So these advanced instruments are becoming more and more sensitive to these quantities and correlations between them. So we need to understand pretty well what's coming out of this fissionable material in order to design better instruments. So I'm going to open up to questions in a minute, but I want to give you a quick summary. Basically, Kyle left us off at this stage where we have fission fragments that are very energetic, they're excited. We start with those in this talk with a lot of excitation energy and angular momentum. Neutron emission carries away most of that excitation energy, and we get maybe 2 to 4 neutrons from a single fission event, usually. And then gamma ray emission carries away the rest of the excitation energy, and then a lot of the angular momentum, which Dr. Vogt will talk about tomorrow. And then at the very end, we're left with fission products that might be unstable to beta decay. And following beta decay, you might get more neutrons and gamma rays. Here are some links to previous work in our group about fission. We're mostly measuring prompt neutron and gamma ray emission in our studies. And with that, I'll open it up to any more questions you all may have. Let's see. The difficulty in measuring initial condition is due to the time scale at which they decay and lose energy, or are there any other reasons as well contributing to that? That's a big contributor, yeah. So when you have fission happen, Kyle talked about it yesterday, the split itself happens within 10 to the minus 20 seconds. That's much faster than any instrument can measure anything. And then neutron emission happens within 10 to the minus 18 to 10 to the minus 15 seconds. That's, again, much faster than any instrument we have. So we never have access to that initial fragment before it starts to decay. I mean, it's also true that it would be difficult to find out the energy and spin of the fragment in the first place, even if it didn't decay pretty quickly. So I hope that helped. Let's see another one. I believe the nuclear reactors are designed around U-235 and 3N reaction. Does this mean that the 3N are delayed neutrons? Given how radioactivity is random, what are the chances of getting prompt neutrons in a reactor, and to what extent do they affect criticality? I'm not a reactor expert, but I would not be surprised if there is a nuclear reaction there, N3N. The way you have it written, those are not delayed neutrons. That would be a reaction where a nucleus absorbs 1 neutron and emits 3 afterward, probably pretty quickly. And if that's a common process, doesn't sound like it would be that common, but maybe common enough to have a real engineering effect, then you would design your reactor around that. Radioactivity is indeed random, and there are chances to get a lot of different things, but there's so much fission happening in a reactor that you're mostly using average quantities. And so you need to have an idea of the time scales that you could be dealing with, but there's enough happening that you can wash away some of those details and still do a decent job. Let's see. The NDA applications you mentioned involving correlated emissions. Are you just talking about neutron multiplicity counting, or are there other ideas being considered involving other correlations? An example of other correlations, which I believe I have a figure of. Yeah, so this figure up top here, what's plotted is the alpha ratio of a plutonium sample, and then the anisotropy of those neutrons that come out of the plutonium sample. As we talked about, neutrons are focused in the direction of fission fragments. And if you have long fission chains, then you'll get a lot of fissions basically at once. And the result will be less anisotropic neutrons, more isotropic neutrons. So the result is that based on the angular distribution of neutrons in a fission chain that you might measure, you can guess what the something about the multiplication and potentially about the content of the sample. That's just one example. In general, these quantities can depend on each other. So in a given fission event, it turns out that if you have more neutrons, you're likely to emit fewer gamma rays. And if you have an instrument that's sensitive to all of those things, then you need to know that. What is the physics behind these relationships? Lots of angular momentum, more gamma rays, and lots of energy, more neutrons. So that tried to answer that back here, but the basic idea is that neutron emission is governed by the strong nuclear force, and that means that it happens on very fast timescales. And also, neutron emission takes away a lot of excitation energy because the binding energy of a neutron is pretty large compared to the excitation energies we're talking about. So each neutron might carry away in total 7 to 8 MeV of excitation energy. Because neutrons don't remove a lot of angular momentum, we're left with a lot of angular momentum, and the only way to remove that is to emit gamma rays. Is it possible to simulate the initial conditions by using Meade field theory approach and validate it by the detectable products such as neutrons and gamma rays? It is possible to simulate initial conditions using Meade field theory approach. Yes, it's then a matter of how good of a job you did. These are, as Kyle talked about yesterday, these are really difficult things to simulate. So people are working on that actively all the time. I think Kyle talked a little bit yesterday about some time-dependent density functional theory stuff as well. Yeah, that people are doing that. It's just really hard. Can you please explain the Cherenkov radiation? I suppose I can tell you what Cherenkov radiation is, and that's when a particle is going faster than the speed of light in that medium. You get a kind of, it's analogous to like a sonic boom. So the speed of light in water is less than the speed of light in vacuum. If you get a very energetic electron, it could go faster than the speed of light in water. That is allowed, and you get Cherenkov radiation out. So that could happen with a beta particle. Do you think we'll ever be able to directly measure events on timescales of 10 to the minus 21 seconds? Or are there physical limitations preventing that from happening? That's an interesting question. I'm going to, let's see. I mean, there certainly are physical limitations. Like, in order to have a process on this time scale, you have to have a requisite amount of energy to make it happen. And to my knowledge, we don't really have detectors that are detecting stuff based on strong interactions right now. In fact, I don't know if that ever will happen. All of our detectors really are using the electromagnetic force in some way. So we're kind of left with looking at the pieces that come out. Can you explain the stability of the material based on the number of protons and neutrons? I guess if you looked at it from a frame of a more excited nucleus is more unstable, which is not incorrect, I suppose. You could say that a more energetic nucleus will generally emit more neutrons. So a fragment with higher excitation energy will have more neutrons. If you're talking about the fission products at the end, I don't know if that necessarily correlates. So at the end, I talked about different groups of fission products. The more unstable fission products will have shorter half-lives, and so they'll decay more quickly. But that doesn't necessarily tell you how unstable the product of that decay will be. So generally, these reactions that corresponds to shorter half-lives might release more energy than the ones down here, but that doesn't necessarily mean that the products of the reactions have less and less energy as you go down. So you could have a reaction in this half-life region that emits neutrons more than a specific reaction in this region, but I'm not sure. Okay, well, we don't have any more questions for now. I'll give it 1 minute, but if you have other questions on the presentation, I'll bring back to the title slide. Here's my email right here. Oh, there's one more. Where can the neutrons be used after being emitted from fission? Well, the neutrons start from the fission fragments, and because it is so soon after the fission, the fragments haven't gone very far yet. So you can effectively think of the neutrons as coming right from the fissioning nucleus. It's basically a point source. Where can they be used? As far as they can go. They're pretty difficult particles to stop because they're electrically neutral. So they're only really going to scatter off things in something like a reactor. Which is more radioactive, an element with shorter half-life or longer half-life? It depends on what you're talking about. If you mean more radioactive, as in like more dangerous from a radiological perspective, an equal amount of material with a short half-life will have a higher activity than the same amount of material with a long half-life. So if you're standing next to, I'd much rather stand next to a 1 kilogram slab of uranium-238 than a 1 kilogram slab of plutonium-238 or something like that. 238 has a shorter half-life. You're getting a lot more decays per second in that way. Of course, there's not all sunshine for our short half-life, for our long half-life rather, products. It means that they are radioactive for much longer, even if the acute radiation dose you might get from them is less. And that means that you have to deal with them over a longer time scale. Okay, I think that's a pretty good place to stop for today. Again, you can email me if you have other questions. And we'll see you all tomorrow for Dr. Ramona Votes talk. I highly encourage you to attend it if you can. She's a very important part of the fission community. And so with that, I will end the presentation. Thanks, guys.
Thank you very much, Nathan. Have a great rest of your day, guys.